Welcome back to QHSE Talks.
Glad to be here.
So imagine holding a standard 20-pound box of printer paper.
Okay, I'm picturing it.
Now, extend your arms straight out in front of you and just hold it there.
Oh, man. That doesn't take long to hurt.
Right. Within seconds, your shoulders start burning, your breathing gets, shallow.
Yeah, and your lower back is suddenly absorbing hundreds of pounds of sheer force.
Exactly. And the crazy thing is you haven't added a single ounce of weight to that box.
Not 1 ounce.
Yet your body is suddenly in this state of total biomechanical crisis.
Mm-hmm.
And that right there, that is the hidden physics of the workplace.
It really is.
So I want to welcome you, the listener, to a highly focused, specialized session tailored just for you. If you are tuning in, you are likely in the trenches right now, preparing to conquer the Associate Safety Professional exam, the ASP.
Which is a beast of a test.
Oh, it really is. And we are dedicating this entirely to your success on that rigorous exam.
And, that test demands far more than just rote memorization. I mean, the AST exam is this comprehensive evaluation of your ability to synthesize safety knowledge.
Right. You can't just memorize flashcards.
Exactly. You have to apply it to real, complex, often really imperfect industrial environments. You have to understand the fundamental mechanics behind the rules.
Well said. So our mission for the session of QHSE Talks is highly specific. We are mastering ASP Domain 3, Topic 5.
The big one.
Yeah, which centers on applying ergonomic principles to manual material handling, or MMH, as you'll see it on the test.
Safe lifting, physical biomechanics, all of that.
The whole 9 yards.
Mm-hmm.
And we've got a formidable stack of sources in front of us today, ranging from ASP exam study guides and the OSHA Construction Safety and Health Handbook to some pretty dense industrial hygiene references.
Very dense.
Yeah. And of course, the comprehensive lifting guidelines from ASH, the National Institute for Occupational Safety and Health.
We really need to ground this in reality, though, before we get to the formulas.
Oh, for sure.
Because, manual material handling isn't just a compliance checklist item. It is literally the single most pervasive cause of occupational fatigue and lower back strains in the American workforce.
Like, it's everywhere.
Everywhere. We are talking about millions of working days lost and billions with a B of dollars in medical costs and compensation.
Wow.
So a safety professional, right? A practitioner of quality, health, safety, and environment, or QHSE. You have to master this material, not just to pass a test, but to fundamentally protect workers from chronic, debilitating pain.
You're essentially the barrier.
Yeah, you are the barrier between a worker having a long, healthy career and them suffering a career-ending injury.
That's a huge responsibility. And I think we hear the word ergonomics so often that it's kind of lost its edge,
Absolutely. It's become a marketing buzzword.
Right. People think of a slightly curved keyboard or like a chair with fancy lumbar support. But for the purposes of the ASP exam, how do our sources truly define the discipline of ergonomics?
Well, the sources define ergonomics as the scientific study of work. Okay. And it is grounded in one non-negotiable principle. The job, the workstation, the tools, and the environment must be adapted to fit the human body.
Rather than the other way around.
Exactly. You never force the human body to conform to the job. It's this huge, multidisciplinary science, drawing from physiology, biomechanics, and engineering.
So it's not just buying a comfy chair.
Far from it. The objective is to optimize human well-being and overall system performance while relentlessly minimizing the risk of musculoskeletal disorders.
It actually makes me think about, modifying a high-performance vehicle.
Oh, I like that. How so?
Well, imagine buying a race car, right? But the pedals are installed a foot out of reach and the steering wheel is mounted under the dashboard.
That'd be a nightmare to drive.
Right. You wouldn't force the driver to contort their spine and stretch their legs until they cramp just to operate the vehicle.
Because their reaction time would plummet.
Yeah, and they'd eventually crash. You would simply remount the pedals and the wheel. So ergonomics is basically engineering the workspace so the human can operate at peak efficiency without physical degradation.
That is a really highly accurate way to visualize it. And it highlights a core theme in the text, which is the distinction between proactive and reactive ergonomics.
Okay, break that down for me.
Historically, industry has been incredibly reactive.
Meaning they wait for something to go wrong.
Yeah. A worker tears a shoulder ligament, an investigation is launched, they find the flaw in the workstation, and then a fix is retrofitted.
Right, closing the barn door after the horse bolted.
Exactly. But the ASP exam prioritizes proactive ergonomics.
Which means intervening before the concrete is even poured.
Precisely. A proactive approach means you, the safety professional, are sitting at the table with the architects, the process engineers, and the purchasing department during the design phase.
Oh, wow. So way early on.
Yeah, of a new facility or a new production line. You are running simulations and evaluating risk factors in the blueprints.
So the goal is zero stress on day one.
Right. To ensure that workflows impose absolutely zero undue biomechanical stress on the workforce from the minute operations begin.
That structural mindset really brings us to the second half of our main topic today, MMH, or manual material handling.
Yeah, the real heavy lifting.
Literally. But I think the average person assumes that just means picking heavy things up off the floor.
Which is a dangerous assumption.
Right, because the regulatory and scientific definitions in our sources are much broader.
They have to be broad, because risk isn't limited to a vertical lift. The sources define MMH as the movement or handling of objects by means of human exertion.
Meaning any exertion.
Any exertion. It explicitly encompasses lifting, lowering, pushing, pulling, carrying, holding, or restraining materials.
Restraining too, like keeping something from falling.
Yes. If a worker's musculoskeletal system is the primary engine moving or resisting a load, it is manual material handling.
Got it.
And because this broad category is the principal source of compensable injuries, we have to meticulously evaluate the work before a worker ever physically engages with a load.
Which leads us right into the pre-lift phase. Before any physical exertion even happens, how do we evaluate the task? I was looking at this OSHA checklist in our sources.
Oh, that's a great checklist.
Yeah, it essentially forces a worker to perform a rapid hazard assessment, right?
Yeah, the pre-lift assessment is a critical administrative control. And the very first question on that OSHA checklist is remarkably simple but so often overlooked.
Which is?
Is the load free to move or is it stuck?
Oh man, I can just picture someone on a loading dock bracing themselves to heave a 50-pound wooden crate, completely unaware that it's like frozen to the pallet or caught on a hidden nail.
Yes, and they throw their entire maximum lifting force against an immovable object.
That sounds terrible for your back.
It is devastating to the human spine.
Yeah.
See, the central nervous system prepares the muscular system for specific kinetic release.
Like it calculates the math before you lift.
Exactly. When that release is violently halted by unexpected resistance, massive shear forces tear across the tendons and the spinal column.
Ouch. Okay, so checking if it's stuck is step one. What else?
The checklist then asks the worker to assess the pathway. Is the floor wet or cluttered?
Right.
Is the drop-off location actually clear? And crucially, can the weight be safely handled by one person?
Now that's interesting. I've noticed a major reliance on that last point in warehouses. The texts talk about getting help, and we hear the phrase team lifting constantly.
Oh, yeah.
You know, two people grab opposite ends of a heavy generator or a massive spool of wire. Based on the rigorous engineering mindset required for the ASP exam, is team lifting considered a permanent, viable solution to an overcapacity load?
That is a vital distinction for you, the listener, to grasp. Team lifting is strictly a temporary administrative Band-Aid.
A Band-Aid, not a cure.
It is absolutely not an engineering control.
Right.
I mean, in theory, it reduces the load by half for each worker, right?
Sure, math says 50-50.
But in practice, it introduces this whole cascade of new, unpredictable hazards.
Because humans aren't perfectly synchronized machines.
Exactly. The lift has to be coordinated with flawless communication.
Which never happens.
Right. If one worker's hand slips, or if they step on a crack and stumble, or if they simply lower their end a fraction of a second too early.
The geometry of the lift violently changes.
Yes. The remaining worker is suddenly subjected to the entire dynamic weight of the load.
And they're probably in a really awkward position when it happens.
Often in a vulnerable, compromised posture, that sudden shock loading is highly conducive to catastrophic muscle tearing. A true safety professional looks to the hierarchy of controls for a permanent solution.
And the pinnacle of that hierarchy is always elimination, right? Can we engineer the hazard out of existence?
That is the gold standard.
So for manual material handling, what does elimination actually look like?
Elimination means restructuring the process so the worker doesn't have to manually manipulate the load at all.
Like using machines.
Exactly. We might increase the weight of raw material shipments to a point where they are exclusively handled by forklifts.
Oh, make it so heavy they can't lift it manually.
Right. Or we integrate mechanical aids like automated conveyors, vacuum hoists, or ball caster tables built directly into the assembly line.
So if someone is manually carrying machined parts from the end of a lathe to a quality control station 30 feet away, the ergonomic solution isn't to teach them a better way to walk with the parts.
No, absolutely not.
The solution is just installing a roller conveyor between the two stations.
Yes, you engineer the physical carrying out of the process entirely.
That makes total sense.
But, if elimination is practically or economically unfeasible, we have to move down the hierarchy to reduction.
Okay, reduction. How do we do that?
Can we reduce the weight, the frequency, or the physical dimensions of the load? We might work with procurement to limit vendors from packing more than 20 pounds of components into a single box.
Oh, just cap the weight before it even arrives.
Right. Or we can physically relocate the storage racks closer to the production floor to slash the carrying distance.
Now, there's a specific principle mentioned in the texts about reducing hand distance. How does changing the shape of a box protect someone's back?
It relates directly to the physics of lever arms and torque, which we touched on with your 20-pound box scenario earlier.
The burning shoulders.
Yeah. The human spine essentially acts as a fulcrum. If a container is excessively wide, the worker is forced to hold the center of mass far away from their body.
And that's bad.
It's terrible.
Yeah.
This long lever arm multiplies the torque applied to the lumbar spine.
So how do we fix it?
By redesigning the object, making the container narrower, or integrating deeply recessed, ergonomically angled handles.
So they can get a grip on it closer to their chest.
Yes. We allow the worker to hold the load center of gravity tight against their own center of gravity, which drastically reduces the biomechanical strain.
Okay, let's follow that logic. We've tried conveyors, we've reduced the vendor package weight, we've added handles.
We've done everything.
Right, but we hit the operational reality where a worker still absolutely must manually lift an object from point A to point B. If it has to be done, we need to explore the exact biomechanics of how to do it safely.
We do. And the cornerstone of manual lifting biomechanics is a concept known as the power zone.
The power zone. It sounds a bit like a sports marketing term,
It really does.
Uh-oh.
But it defines the absolute optimal operating envelope for the human body.
Okay, where is the zone?
The power zone is roughly the area between mid-thigh and mid-chest height.
Mid-thigh to mid-chest.
Functionally, this is where the human musculoskeletal system exhibits its maximum mechanical advantage and greatest stability.
So it's where we're strongest.
Exactly. The skeletal structure is aligned to absorb compression, and the major muscle groups are engaged without being stretched to their vulnerable limits.
Got it.
The sources dictate that strenuous manual lifts must be confined to this vertical zone. Furthermore, workers should never reach more than 15 inches in front of their bodies to grasp or manipulate materials.
Wow, just 15 inches. That's barely more than a foot.
Yep. Keep it close.
Okay, so keeping the materials within that mid-thigh to mid-chest window and keeping them within 15 inches. Let's walk through the actual kinetic sequence of a basic diagonal lift as outlined in the OSHA standards.
Right. The sequence begins with positioning. The worker stands as close to the load as physically possible, establishing a solid base of support with feet shoulder width apart.
Which is roughly 8 to 12 inches.
Right, roughly. One foot is often placed slightly forward for dynamic balance. They hinge at the hips and bend the knees to lower themselves.
And then they grab it.
They secure a firm, full hand grasp on opposite corners of the load.
Okay, and then the lift itself.
The critical phase is the upward thrust.
Yeah.
The back is kept in a straight, neutral posture, and the powerful muscles of the lugs and glutes are engaged to drive the body upward, lifting the load vertically while keeping it pinned close to the torso.
And as they lift, we arrive at what I view as the most unforgiving rule in material handling, like the cardinal rule regarding the spine.
Oh, absolutely.
The guidelines state vehemently, do not twist or turn the torso until the object is fully in the carrying position.
Never twist.
Why is the human spine so intolerant of rotation under load? Like, why is that so dangerous?
It comes down to the anatomy of the spinal discs, specifically the intervertebral discs in the lumbar region, like L5-S1.
Those are the ones down at the base of the spine, right?
Yes. They bear the absolute brunt of lifting forces. These discs are essentially tough, fibrous rings surrounding a gel-like center.
Kind of like a jelly donut.
Exactly like that. And they are remarkably well engineered to handle straight vertical compression. When you lift straight up, the force is distributed evenly across the disc.
But twisting throws that distribution off. I actually felt this years ago helping a friend move a heavy sleeper sofa.
Oh, couches are the worst.
They really are. I had my end lifted, And instead of taking a step to navigate a doorway, I just rotated my waist.
Just twisted your torso.
Yeah, and the pain was instantaneous, like a lightning bolt.
What you experienced was the destructive nature of shear force.
Sheer force.
When you rotate your spine while it is under a heavy compressive load, you subject those fibrous rings to shear, grinding friction. The fibers are stretched diagonally, significantly weakening the structural integrity of the disc wall.
Which leads to the jelly coming out.
Unfortunately, yes.
Yeah.
This is the exact mechanism that leads to ruptured or herniated discs, where that inner gel bulges out and compresses the spinal nerves. It is an excruciating and often permanent injury.
So the behavioral control is simple, even if it takes conscious effort to build the habit. If you are holding a load and need to place it on a table to your left, you lock your torso in a neutral, forward-facing posture, and you physically pick up your feet to pivot your entire body.
Yes. You use your feet to navigate, treating your torso and the load as a single, rigid column. It preserves the straight compressive load and eliminates the shear force entirely.
Now, regarding that lifting posture, I found a detail in the sources that completely upends a piece of advice we've all heard since childhood.
I think I know which one you're talking about.
Everyone says, lift with your knees, not your back.
Right. Culturally, we interpret that as dropping into a deep, full squat.
Yeah, bringing our hips almost to our heels to keep the back perfectly vertical. But the texts detail a powerlifting technique that explicitly warns against bending the knees below a 120-degree angle.
Yes, they do.
Why does that deep squat suddenly become an ergonomic hazard?
Because that cultural misconception is responsible for a massive number of knee injuries.
Really?
From a biomechanical perspective, when you drop into a deep, full squat, flexing the knees well past 120 degrees, you place an extreme hypercompressive load on the patellofemoral joint.
The kneecap.
The kneecap. You are essentially grinding the cartilage.
Yikes. And beyond the knee joint stress, it seems like you'd get stuck down there, like it's hard to get back up.
You do. You lose all mechanical advantage. Your powerful gluteal muscles and quadriceps are stretched to a point where they cannot generate effective upward thrust.
So how do you get up with the weight?
To initiate the lift from that deep hole, the worker inevitably has to pitch their upper body forward to generate momentum, which wildly recruits the lower back muscles anyway.
Oh, so you end up using your back anyway.
Exactly.
Oh.
So the deep squat destroys the knees and ultimately forces the back to do the hardest part of the initial lift.
That's wild. So what is the powerlifting technique then?
It advocates for a partial squat, maintaining a slight bend of no more than 120 degrees. This keeps the hips higher, keeping the glutes and hamstrings in their optimal firing range.
So you can actually use those leg muscles.
Right, allowing for a smooth, powerful vertical drive without jerking the lumbar spine.
That distinction alone is worth the price of admission for the exam. We've established the qualitative rules, utilize the parry zone, minimize the lever arm, never twist under load, use your feet to turn, and avoid the deep squat.
Those are the golden rules.
But the AST exam doesn't just want qualitative advice, does it? We have to quantify the hazard. We need the mathematical framework to prove a lift is unsafe.
And that imperative brings us to the absolute centerpiece of ergonomic mathematics. It's heavily featured in both Domain 1 for Advanced Sciences and Domain 3. We are talking about their revised MOH lifting equation.
Okay, here we go. The ultimate goal of this equation is to calculate the recommended weight limit, or the RWL.
Correct.
This formula determines the exact maximum weight a healthy worker can safely lift over the course of a standard 8-hour shift without elevating their risk of lower back pain.
That's the goal.
But when you look at the formula RWL equals LC times HM times VM times DM times AM times FM times CM, it looks incredibly daunting.
It is a long string of 7 variables, I'll admit.
Yeah.
But the underlying logic is quite elegant when you break it down.
I found it helps to think of the Noah-ish equation like a video game health bar.
Oh, I love analogies. Let's hear it.
Okay, so your baseline lifting capacity under perfect, pristine laboratory conditions is 100%, right?
Mm-hmm.
In the equation, this baseline is the load constant, or LC.
Yeah.
But a real industrial environment is never perfect. Every suboptimal condition like reaching too far, starting the lift from the floor, twisting, or dealing with a slippery box acts as a penalty.
Exactly.
In the math, each penalty is a multiplier represented by a fraction, a decimal less than 1. So with every awkward factor you introduce, you multiply your baseline capacity by a fraction, shrinking your safe weight limit down further and further.
That analogy captures the mathematical reality perfectly.
So what is that baseline? What's the LC?
The load constant, the LC, is established by NIOSH at exactly 51 pounds.
51 pounds.
That 51 pounds represents the theoretical maximum load a human should lift when every single environmental and physical condition is flawless.
Flawless, meaning?
It means the load is directly in front of the body at knuckle height, requiring almost no vertical travel with zero twisting, a perfect grip, and performed only occasionally.
So basically never.
Basically never in the real world. If all those conditions are met, all the multipliers equal 1 and the RWL remains 51 pounds. But as you noted, industrial reality is full of penalties. Let's dissect how each of these specific variables degrades that human capacity.
Okay, I'll start us off with the geometry. The first penalty factor is HM, the horizontal multiplier. We talked about lever arms earlier. I assume this multiplier mathematically penalizes the worker for how far the center of the load is from their spine.
Precisely. The horizontal multiplier calculates the horizontal distance from the midpoint between the ankles to a point projected on the floor directly below the center of the hands grasping the object.
Wow, that's a very specific measurement.
It has to be. The ideal minimum distance is 10 inches. Anything beyond that 10-inch mark begins to drop the multiplier below 1.
So if a worker has to reach, say, 20 inches across a deep conveyor belt to grab a part?
The lever arm is doubled, the torque on the L5S1 disc skyrockets, and the HM fraction severely slashes the final safe lifting weight.
Okay, so we've solved for how far away the object is. But what about the terrain of the workstation? Does the starting height of the lift change the physics?
Oh, dramatically.
That brings us to VM, the vertical multiplier.
The vertical starting height is crucial. Now Slight determined that the optimal starting height for a lift is 30 inches off the floor.
30 inches, which aligns perfectly with that biomechanical power zone we talked about.
Exactly. Lifts initiating at this height require minimal trunk flexion and allow the legs to do the work.
But what if it's lower, like deadlifting a box off the concrete floor?
Or higher, like pulling a component off a shelf above shoulder height. In both cases, the worker is operating outside their strongest muscular range.
So they get penalized.
Yes. The further the starting point deviates from that 30-inch ideal, whether up or down, the harsher the penalty applied to the vertical multiplier.
That makes intuitive sense. Now, if I start a lift at that optimal 30-inch waist height, but I have to lift the object all the way up over my head to stack it on a high rack, the physical distance traveled must drain my energy. How does the equation account for that?
That is captured by DM, the distance multiplier. This variable measures the total vertical travel of the object from its starting point to its destination.
So lifting at a few inches versus a few feet.
Right. Lifting a load a few inches requires a brief muscular contraction. Moving that same load from the floor to a 60-inch high shelf requires sustained muscular exertion.
Burning way more calories.
Burning significantly more metabolic energy and inducing cardiovascular fatigue much faster. The equation applies a penalty based on the total inches of vertical travel. Greater distances yield lower multipliers.
Okay, going back to my disastrous couch moving scenario, if I twist my spine while holding the load, that health bar must absolutely plummet. The asymmetric multiplier, or AM, has to be a major factor.
The AM is arguably one of the most punitive multipliers in the formula because it addresses that dangerous shear force we analyzed earlier.
Right, the jelly donut squishing.
Yeah. Asymmetry measures the angle of twisting in degrees away from the straight sagittal plane. NIOH heavily penalizes any rotational movement.
So if I pick up a tote from a cart and have to twist my torso 90 degrees to place it on a workbench,
the asymmetric multiplier drops precipitously. The equation's math is designed to flag twisting as basically unacceptable.
So how do you fix it proactively?
In proactive ergonomics, the solution is to rearrange the layout, perhaps moving the cart directly in front of the workbench, so the asymmetric angle returns to zero.
Simple but effective. Now, so far we've looked at the physics of a single lift, but I can imagine frequency changes everything.
Oh, it changes the entire metabolic demand of the job.
Right, because if I lift a 40-pound box once during my shift, I'll be fine. But if I am on a fast-paced sorting line and I have to lift that same 40-pound box every 30 seconds for an 8-hour shift, my muscles are going to experience total cellular failure.
Yes, they will.
How does the FM, the frequency multiplier, quantify that exhaustion?
The frequency multiplier is a complex variable because it assesses 3 interconnected factors: the number of lifts per minute, the total duration of the lifting task, categorized as short, moderate, or long duration, and the vertical height of the lift.
Why does it need all three?
Because a muscle needs recovery time to clear out metabolic byproducts like lactic acid and replenish cellular energy stores.
Ah, okay.
High-frequency lifting denies the muscle this recovery window, leading to rapid compounding fatigue and vastly increasing the likelihood of injury. The FM applies severe fractional penalties as the lifts per minute increase and as the shift drags on.
Makes sense. Now there is one final variable, and it has to account for how the worker is physically connecting to the load. CM, the coupling multiplier.
Yes, the grip.
I assume this differentiates between grabbing a well-designed handle versus trying to palm a slippery, oddly shaped object.
Exactly. Coupling refers to the quality of the grip, categorized generally as good, fair, or poor.
What's a good grip?
A good coupling means the container has optimally designed, comfortable handles that allow the worker to employ a full power grip.
A power grip?
Power grip wraps all the fingers and the thumb around the handle, locking the load in place utilizing the thick, powerful musculature of the forearm.
I read a genuinely shocking statistic in the sources regarding a different type of grip, the pinch grip.
Yes. The texts point out that utilizing a pinch grip generates 5 times the physical stress on the body compared to a power grip.
5 times the stress just from holding it differently. How does that work at a physiological level?
Think about the mechanics of a pinch grip. You are relying solely on the very tips of your fingers and your thumb, squeezing the smooth edges of a box to generate enough friction to prevent it from sliding out of your hands.
Right, like holding a heavy book by the spine.
Yeah. You are isolating the tiny, delicate tendons in your fingers and wrist. Furthermore, you have to exert a massive amount of static gripping force before you even begin the vertical work of lifting the dead weight.
Oh, because if you don't squeeze hard enough, you just drop it.
Exactly. This constant high-tension squeezing rapidly exhausts the small forearm flexors, dramatically increasing the risk of dropping the load or developing inflammatory conditions in the tendons. A poor grip requiring a pinch results in a significantly reduced coupling multiplier.
So to bring the mathematical reality of this into focus, let's say an employee is working in a poorly designed warehouse.
Okay, paint the picture.
They have to reach far forward across a pallet that's a low horizontal multiplier. They have to pick up a box off the ground low vertical multiplier, lift it up to a high shelf low distance multiplier, twist their spine 45 degrees to place it, terrible asymmetric multiplier, perform this motion continuously all afternoon low frequency multiplier, and the boxes have no handles, forcing a pinch grip low coupling multiplier.
That is a nightmare scenario.
Right, so that theoretical baseline of 51 pounds is being multiplied by fraction after fraction. By the end of the calculation, that recommended weight limit might be slashed down to a mere 10 or 12 pounds.
That is exactly how the math works in practice. And here's the critical safety juncture. If the NIOS equation dictates that the safe recommended weight limit for that specific awkward motion is 12 pounds, but the box of parts actually weighs 35 pounds, you have identified a hazardous mismatch.
The job is literally too hard for the human body.
The physical demands of the job are objectively exceeding the physiological capabilities of the workforce.
So as a safety professional, what is your move? If the math proves the manual lift is unsafe and we can't change the 35-pound weight of the parts, what do?
You implement engineering controls to eliminate the manual lifting phase. You introduce mechanical assists.
Wheels, basically.
Wheels, hoists, carts. And if a worker must move that 35-pound load across the facility, they shouldn't be carrying it. They should be using equipment, which pivots our focus to the mechanics of pushing, pulling, and real transport.
And this is a scenario every safety professional encounters. I've got a heavily loaded four-wheeled utility cart in a manufacturing plant.
Very common.
Do I instruct the worker to walk in front of it and pull it behind them, or stand behind it and push it?
You instruct them to push. Emphatically and universally, pushing a load is biomechanically far superior to pulling a load.
What's the physiological difference? It seems like it requires the same amount of force to move the mass either way.
It's about how that force is generated and transferred through the body. When you push a heavy cart, you lean your center of gravity forward into the load.
Oh, so you're using your body weight.
Yes. And this posture naturally engages the largest, most robust muscle groups in your body, the quadriceps, the hamstrings, and the glutes. You are using your legs as the engine. Crucially, pushing allows you to maintain a neutral, forward-facing spinal alignment, transferring the force straight through your skeletal frame.
And if I turn around and try to pull that same cart?
The mechanics deteriorate immediately. First, to pull a cart while walking forward, you have to reach your arm behind you, placing immense unnatural stress on the anterior capsule of the shoulder joint and the labrum.
Because your arm is basically twisted backward?
Right. You are relying heavily on the smaller, weaker muscles of the rotator cuff and the arm to tow the weight. Second, workers pulling carts inevitably twist their torso to look back over their shoulder to steer, introducing that dangerous spinal shear force we talked about.
Oh, yeah, you have to see where you're going.
Exactly. And finally, if the cart's wheel catches on a floor joint and suddenly stops, the momentum of the heavy cart violently yanks the worker backward.
Like a dog hitting the end of a leash.
Exactly like that. It frequently results in severe shoulder dislocations or lower back strains. Pulling is an ergonomic liability.
So the fundamental rule for the ASP exam is clear. Convert lifting to pushing whenever feasible, and rigorously mandate pushing over pulling. But we can also engineer the carts themselves to optimize that pushing action, right? The guidelines mention specific design parameters for the equipment.
Absolutely. The interface between the worker and the equipment is vital. Carts should be equipped with variable height handles or vertical handlebars.
Because the workforce isn't a uniform height. A handle that is perfect for someone who is 6'2" is going to be terrible for someone who is 5'4".
Exactly. The biomechanical goal is for any employee, regardless of their stature, to be able to grasp the handles while maintaining a natural elbow bend of roughly 80 to 100 degrees.
Why that specific angle?
That specific angular range allows for the most efficient transfer of kinetic energy from the legs through a braced torso and out through the arms into the cart, without hyperextending the elbows or straining the shoulders.
That makes total sense. Now, the sources also pivot from the cart to the environment itself, focusing heavily on wheels and floor conditions.
Right, because the physics of moving a cart is entirely dependent on overcoming static and kinetic friction. Ergonomic design dictates utilizing large diameter wheels and casters.
Big wheels are better.
Always. A larger wheel rolls much more efficiently over minor debris, elevator thresholds, or uneven concrete, drastically reducing the initial breakaway force the worker must exert to get the cart moving.
So it's easier to start pushing.
Yes. And this underscores why facility maintenance is an ergonomic issue. If a warehouse floor is degraded, full of potholes, deep cracks, or scattered pallets, the friction coefficient skyrockets.
The floor is fighting the worker.
The worker has to burn massive amounts of energy fighting the terrain. Repairing and sweeping floors is just as much an ergonomic intervention as buying a new cart.
Wow, I never thought of a broom as ergonomic equipment. Let's focus on a piece of equipment that is ubiquitous across every industry. The two-wheeled hand truck, or dolly.
The classic.
It's a simple lever on wheels, but the texts highlight very specific operational rules because they are involved in so many accidents.
Their simplicity breeds complacency. The safe operation of a hand truck begins with an administrative control, the pre-operational inspection.
What are they looking for?
Before loading, the worker must physically verify the tire pressure, ensure the axle isn't bent, and check the structural integrity of the nose plate. Furthermore, every piece of material handling equipment has a manufacturer-rated load capacity.
Which people probably ignore all the time.
And that's dangerous. Exceeding that capacity compromises the balance and structural safety of the unit.
When it comes to actually stacking the materials on the hand truck, is there a specific protocol, like heavy stuff on the bottom?
Yes, it's an exercise in center of gravity management. You must always place the heaviest, bulkiest items flat on the bottom, directly above the axle, and stack the lighter, smaller boxes on top.
Keeps it grounded.
It keeps the center of gravity as low as possible, preventing the hand truck from becoming top-heavy and dangerously unstable during transit. If the load is irregular, ratchet straps should be utilized to secure it to the frame.
And when they actually tilt it back to move?
When the worker is ready to move, they shouldn't just grab the handles and heave backward using their lower back. They should utilize the mechanical advantage of the tool.
By using their foot, right?
Yes. By placing one foot firmly on the axle or the bottom edge of the frame and using their own body weight to lever the load back into the tilted travel position.
Okay, we have our properly stacked hand truck, and we're moving. But I hit a section in the manual regarding ramps that completely stopped me.
Let me guess. Going down the ramp.
Yes. It feels incredibly counterintuitive. The rule states, if traveling down a ramp, keep the load in front. If traveling up a ramp, keep the load behind you.
Yeah, that trips a lot of people up.
Wait, going downhill, if I keep a heavily loaded cart in front of me, why wouldn't gravity just rip it out of my hands and pull me down the slope?
It does sound backward, until you analyze the physics and the injury data. Let's examine the downhill scenario first. Imagine you are walking down a steep ramp with a heavily loaded hand truck trailing behind you.
Okay.
Gravity is pulling the mass of that load aggressively down the slope, directly toward your back.
So its momentum is essentially chasing me.
Exactly. And if that load gains too much momentum, or if you simply lose your grip, the hand truck will accelerate down the ramp, violently striking the back of your legs, potentially crushing your Achilles tendons or knocking you face forward onto the concrete.
Okay, that sounds horrible.
By keeping the load in front of you as you travel down the ramp, you remain in complete physical control of the system. You tilt the truck back, lean your own body weight backward into the hill, and use the massive strength of your quadriceps to act as a braking system, safely pacing the descent.
Ah. The legs act as the brakes, and the load is never in a position to run you over. That makes perfect sense. What about the uphill journey? Why do I drag it behind me?
Think about the mechanical disadvantage of trying to push a heavy wheeled load up a steep incline in front of you. Your arms and chest are fighting against the full vector of gravity.
It's incredibly exhausting.
Yes. More importantly, if the load proves too heavy to push, or if your boots lose traction on a wet spot on the ramp, you will fall forward, and the hand truck will instantly roll backward, directly over your body, causing severe crushing injuries.
Because you're below the load. The crush zone is essentially below the load.
Exactly. By keeping the hand truck behind you when ascending a ramp, you change the dynamic. You lean your torso forward, up the hill, and use your body weight to pull the load up behind you.
And if you slip?
If you slip, or if you lose your grip, the load rolls harmlessly away from you, down the ramp. It might damage the materials, but your body is completely clear of the crush zone.
It's all about designing the work process so that if a failure occurs, physics dictates the human is out of harm's way.
Exactly.
And speaking of equipment failure, there's a vital administrative element we need to discuss regarding these mechanical assists.
Yes, we can't forget maintenance. The entire ergonomic program hinges on rigorous preventative maintenance. Forklifts, pallet jacks, hydraulic lift tables, and hand trucks must be maintained flawlessly.
Because if the tool is broken, the worker is basically back to square one.
It is often worse than square one.
Really? Why?
Because industrial production schedules are relentless. If a motorized pallet jack breaks down and a maintenance protocol isn't immediately initiated, the workers on the floor will rarely halt production to wait for a repair.
They still have quotas to hit.
To meet their quotas, they will invariably revert to manual lifting. They will attempt to physically carry heavy components that were explicitly analyzed and designated by safety engineers to be moved strictly by machines.
Oh man, so they're lifting things that are way too heavy.
This behavioral adaptation to broken equipment is a massive driver of catastrophic, acute musculoskeletal injuries. Ensuring that ergonomic equipment is fully operational is a non-negotiable metric for the safety professional.
We have covered an immense amount of ground today, from cellular muscle fatigue to the physics of inclined planes.
It's a lot to absorb.
It really is. So, for you, the listener, dedicating your time to conquering Domain 3, Topic 5 on the ASP exam, let's distill this session into the core actionable takeaways.
Sounds good.
First, understand the absolute core philosophy of ergonomics. Adapt the workstation, the tools, and the environment to fit the human body. Prioritize proactive ergonomics by engineering out hazards during the architectural design phase, rather than reacting to injuries after the fact.
Spot on.
Second, strictly adhere to the hierarchy of controls. Relentlessly seek to eliminate the manual lift entirely through automation or mechanical equipment. If manual handling is unavoidable, reduce the weight, minimize travel distances, and redesign containers to keep the load's center of gravity close to the body. Recognize that team lifting is a hazardous, temporary administrative measure, not a permanent engineering solution.
Don't fall for the team lifting trap on the exam.
Right. Third, master the biomechanics of the lift. Keep all heavy materials within the power zone between mid-thigh and mid-chest. Never reach out further than 15 inches. Utilize the powerlifting technique. Maintain a slight knee bend of no more than 120 degrees to preserve mechanical advantage and protect the knee joints. And obey the most critical rule of the spine. Never twist your torso while under a compressive load. Pivot your feet to change direction.
Pivot the feet, save the discs.
Fourth, memorize the variables and the purpose of the Anish lifting equation. Understand that the baseline 51-pound load constant is systematically degraded by multiplier penalties involving horizontal distance, vertical starting height, total distance traveled, asymmetric twisting, frequency of the task. As we conclude this session of QHSE Talks, we always want to leave you with a final, thought-provoking concept to consider as you step back into your own facility, something that builds on the science we've discussed today.
Consider the hidden cognitive load imposed by a poorly designed workspace.
Cognitive load, like mental exhaustion.
Exactly. Throughout this session, we have analyzed ergonomics through the lens of physical degradation, the shear forces on the lumbar discs, the friction in the knee joints, the exhaustion of the forearm flexors. But when a process forces a worker into an unnatural posture or demands they maintain a precarious pinch grip on a slippery component, we are not merely draining their muscular stamina.
We're draining their brain, too.
We are actively draining their mental bandwidth. In a hazardous ergonomic environment, the worker must dedicate a significant portion of their conscious brain power simply to monitoring their own body, constantly self-correcting to avoid pain or acute injury.
They're constantly thinking, don't hurt my back, don't hurt my back.
Exactly. However, when proactive ergonomics are successfully implemented, when the workstation fits the human form flawlessly, the physical act of working becomes seamless and subconscious. It liberates the worker's mind.
That's a powerful way to look at it.
They can dedicate their full cognitive capacity to the precision, quality, and efficiency of their actual work. So, as you evaluate your operations, ask yourself a difficult question. How many quality control errors, dropped parts, or momentary lapses in judgment on your floor are not behavioral failures, but rather the silent symptoms of hidden ergonomic fatigue?
That reframes the entire discipline for me. Ergonomics isn't merely an injury prevention program. It is foundational to operational excellence and quality control. Thank you for investing your time in this session of QHSE Talks. We trust this intensive exploration of manual material handling has armed you with the deep understanding necessary to excel on the ASP exam, and more importantly, to fundamentally improve the lives of the workers you protect. Keep studying the science, keep pushing for proactive safety, and we will catch you on the next session.